Today, probably the most important lecture of this course, verification, validation. This is the essence that you should learn through this course. Very, very important. Also, stuff that you need to keep in the back of your head now that you are about to join a project group, finding a project work. So, validation, verification, essential. I have put out last year's reports, so you can have a look at these, what they did last year. Don't feel bounded by anything. You can jump to any problem, whatever you want. Just discuss it with me, and then we can always design a project work for you. Preferably for a person in each group. But I am not fanatic about it, so we can discuss it. But 4, that's sort of an ideal group. No more than 4. Being alone in one group, not funny. Possible, but not fun. So I would recommend, say, 3, 4. That should be okay. You have been given a project report template, sadly only in Word. I'll see if I can find one in LaTeX as well. That could be nice. And typically, these templates, that's what you have to deal with when you are writing a scientific article, depending on the journal, of course. So this is something that you have to copy down and use when you are writing your report. Maximum 10 pages, no more than 10 pages in the report. You could use appendixes, as many as you like. That's okay, but they're sort of not part of the report actually. It will be more part of helping next year's student that might pursue your topic, doing the same thing and continuing where you left off. So in the appendix there you can put input files, block mesh dict files, whatever that could help any person that want to do the same as you have been doing. Evaluation form, it's an old one, but more or less we still using it. It's sort of something that I give the censors. Remember, the poster session lasts for 2 hours. You have to stand there in front of it, defending your poster, answering questions to any visitors that might come by. Some of these visitors will then be censors, and you will be graded as a group, as an entire group. So the whole group gets the same grade, of course. And then I will ask them to sort of have a look at, well, this is the project report. Here is the poster. Sort of some points that they should look at. The censors will not be bound by these, but sort of a helping tool for the censors. At least you should be aware of the rules here. Okay? So have a look at them. Think these kinds of thoughts when you are designing your poster, writing the report. Nobody has said that the poster and the report has to be sort of one-to-one. Not so at all. So the report, that's a little more boring scientific piece of work. The poster can be more catching the eye, more interesting results. Maybe something that totally doesn't work, but it looks very fancy. You can have a lot of fun with the poster. It's more sort of a PR stunt than the actual scientific results. They are in the report. Yep.
Who are the censors? PhD students?
The censors are anonymous, secret agents. You don't know.
Okay, but what type of people will you talk to?
You will talk to people who know CFD. I can promise you that. So the same goes when you are writing the report. This is also important when you write your report now for the project, for the master. You should always keep in mind who are my readers? Who is going to read this boring thing? then you should think the rest of the class is going to read it. You are writing for the rest of the class. That means you don't have to start by developing the entire Navier-Stokes. People know it already, so don't start too easy. And also, don't start too advanced. So say if you want to hit and do a project, you are using a special version of a K-epsilon model, some renormalization group theory that nobody else has heard about. Okay, then you have to explain that theory. People know turbulence, they know K-epsilon, the standard, but they don't know the advanced models that you have been picking. So think who is going to read this? What level should you be writing? That's important. And the same goes then for the sensors. They should be on the same level as this class. Okay? Other questions? Good. Yeah, you can read for yourself. The report should then have the standard setup of a classical report, sort of introduction, theory part, theory chapter, planning, scope, definition. I think these two actually should have been switched if you think of the sequence. Planning, scope, definition, here we are talking introduction. Describing why is this important, also what's the state of the art in the world today on this topic. That's the introduction. Then method, theory. No more theory than you actually need in the discussion part later on to describe or explain your crazy results. Then you need some theory to back it up. Literature study, yeah, also this one could have been in introduction actually. Results, discussion. Typically I would recommend you join these two chapters together. So you call the chapter results and discussion. It's more for experimental work that you will have one result part and then one huge discussion afterwards. With CFD, simulation projects, I would say it's a little boring to present all the results and then do this discussion afterwards, because then you have to sort of repeat the results anyway. So call it results and discussion. At least that's my recommendation. But you're free to do it whatever you want. Conclusion, of course. And then if you want further work, that's an option, of course. For the poster, you have been given also a little bit poster tips. You will be given a group number, of course. So put the number on as a title, and then of course the name of all the members of your group, and then some straightforward, easy principle sketches, what's going on, a list of assumptions, simplifications, whatever, and then theory, as it says here, enough so your classmates can understand what you are talking about. And some results, concluding remarks should also be present. And of course, English, always English. These are, as I say, guidelines, so they're not absolute. The poster is to be nailed to a board 120 by 1 meters. So it's just a construction plate actually, so you can have it landscape or portrait, your choice. So you have the sizes here. Should be 1 by 1.2, and don't pay the price for printing a professional poster. I mean, this size would be, what is it, A0 or something? Very big. Expensive, costs you 1,000, so don't do it. Instead, you base your printout on either A4 or also we have A3 color printers available. The way you can do it is the following. You fire up any favorite text editor you use, Word, PowerPoint, whatever. Then you specify the page size, 1 by 1.2 meters as a paper size. And then you just fill whatever you want into that big sheet, one single page. And then you print to a PDF file. If you bring that PDF file to me, I can print it out on a color printer, and then he will automatically split it up into A3 papers. Then you have to use some scissors and glue and jigsaw puzzle it together into one big paper. That's perfect. That's just nice. You don't have to. If you prefer, you can design your own poster by separate sheets, either A4 or A3, and then just put them next to each other, something like this. That will be okay. Of course, you can't have one continuous line then. That's not so easy. So then they will be sort of separate blocks, but then that can be also nice. Totally up to you. This, of course, would be easier because here, the night before the presentation, you find you have a very big mistake here. You have to change it a little bit. Then you only have to print this paper out again. If you have made a very big poster, then you're in trouble. Then you have to print out the entire poster again. Worst case scenario. So I will recommend have the poster ready, say a couple of days in advance of the presentation, so that we will have time to print it and even maybe time to reprint it if you find any errors. But don't pay for it yourself, it's too expensive. Also, what I want is a draft of the report 2 days in advance before the presentation, so that I can prepare my censors. They should have some pre-warning what the topic is about, so they can prepare some nasty questions for you, of course. Okay. The topic that you can choose is very, very open, very wide. So I will not limit you much. I will give a warning here and now. Don't think too advanced. It doesn't have to be too complex. It can be very, very simple. One-dimensional case, that's a beautiful test case for that matter, for open foam. I've had one group did the testing of different turbulence models, just one line from wall to wall. That was very interesting, very simple. Then you have very quick and fast simulations, steady state, one-dimensional. It took seconds to do one simulation, and they had a whole bunch of interesting results. Instead of dreaming up three-dimensional, transient, turbulent, multi-phase flow. Thank you very much, you're in trouble before you begin. So that will be my job, to sort of calm you down here. Hey, be realistic about this. So talk to me about it. We will have you have to have some continuous discussion about your project, but try to think easy, simple. And as the topic will be today, find something to validate and verify your results with. This is the most dangerous thing about CFD. Any monkey can hit the run button and get some beautiful colors out of it, but is it true? Or how true are they? That's the problem. So today, verification, validation, and tomorrow I will then give you, well, you have already been given another exercise that we can play around with. Meaning tomorrow you may do some exercise, we may have some discussion if you start forming groups and have some ideas what you can and cannot do, then I will be available tomorrow. Thursday morning, lecture. We're still missing one tutorial. I want to show you how to program C++, make your own version of OpenFOAM. So that's also something I want to show you, and some hopefully some more unstructured mesh systems, and some final tips and tricks. Maybe we can do that today. Okay, any questions before we continue? Yes?
Do you know when the presentation will be?
Yes, I think we do, because that one is scheduled officially as an oral exam. And didn't we have it here somewhere? No, not here. Let's see if we can find it. Here we go. Here we go. And here we go. TEP4545. 13th of November. Sorry, you don't see it. 13th of November. So the end of November.
Oh, 30th.
Yeah, 30th.
Oh.
Yeah.
Is it decided?
From the official office, yes. We can sort of play a little bit around with it if we want to. But then we can move it a couple of days either way if we want to. And because then we don't tell anybody. I mean, this is our oral exam, and we don't have any guides or any officials that's going to interfere. So yes, we can play a little bit around with it, but only a couple of days or so in either way. If any of you is going to be away, then by all means tell me. If you really say, "Ooh, I'm going to give birth that day," or whatever, then let me know. Then we can maybe move it a little bit. It's not a total disaster if one of the group members is away. Remember, the entire group is sort of defending the poster, the report. So if you get a question when you're standing there talking and chatting, drinking coffee to any bypassers, and you get a question that you really can't answer, it's totally fair to say, "Sorry, my colleague, he went into these details, ask him." That's okay. So it's the entire group that sort of answers. So if you don't answer personally, then some of the other might sort of step in and help you. So that means if one of the group members is away, then the other group members has to be dead certain that they know what the absent person has been doing. Okay? So for now, we let it be on the 30th of November. Unless I hear otherwise, we will keep it there. And the time will be from 9 to 12. Okay? Other questions? No? Then we continue with, if I can get it up here somewhere. No? That was strange. Let's try. No. Something wrong here. Okay, I have to do it like this then. Post-processing, as you have seen and as I have discussed already, dangerous. And it's very easy then to create a lot of fancy results. Contour plots, vector plots, 3D plots, even animations. very easy, very impressive, very convincing, and they may be totally rubbish. So that's the problem. What we can do also, not making pretty pictures, is of course to calculate something that we are interested in depending on the problem, like drag lift forces, vorticity, integral values, whatever. So we need something here that we can set as an answer 2 lines under. That would be very nice, but that depends on the problem, of course. And always remember, the analysis can take a long time. The simulation can take time, but also keep some time on the other side, because yes, you are going to spend a long time to produce results that can be reliable. So here we go. How can we trust the results? How can we trust any simulation, any solution that we have achieved? We have some errors. Of course we have errors. We have numerical errors. We can have errors in the code. That's not funny, especially since we are sort of it's not our fault. Somebody else has been doing the coding. And of course human errors, meaning we do something stupid as say input values, for instance. You don't use the software correctly. We have things that are not precise, that we have to make some choices, things that we really don't know, like fluid properties. What kind of fluid is this? How is the viscosity? Is it depending on the temperature or not? And things like that. The errors, we sort of can have a control. Coding, sort of, for us, we have to believe it, of course. We don't go checking the C++ code for the entire OpenFOAM. Of course we don't. We can check, of course, how we do the how we use the software, and we can investigate the numerical errors, playing around with different grids, check that the residuals are close to 0, and so on. So this also is something that we have talked about. The resolution, spatial resolution, might be important. We found something that the cell Reynolds number has to be smaller than 2. Remember? Okay, so check the cell Reynolds number then, for instance. Then we have some messed up mesh system on unstructured. We have not 90-degree angles, so there maybe we have to play around with different grids, see if that can improve the solution. Then the boundaries will always contain errors. We send in k epsilon values that are not realistic. The outlet, we use typically derivative equal to 0. That's actually not correct. So we'll have an error that will hopefully not propagate too far upstream and destroy our area of interest and so on. So putting the inlet, outlet far away, interesting and important, of course. Make sure that the solution is converged. Using too much dissipation, first order upwind scheme, bad idea. Very stable, but don't do it. Told you many times. Inadequate boundary conditions. Maybe you use a pressure difference as a driving force. Maybe you should have used volume flow in, or vice versa. Too large time steps. You skip the entire physics in one time step. A lot of the transient behavior disappears. You don't see it. Bad. Typically, what you can do with implicit schemes, they are very stable. You can take large time steps. Don't do it. Bad models. This is also something that we have played around with turbulence. Multi-phase flow chemical is not something we have studied too much so far, but turbulence, you know already. You can play around with turbulence models and get any answer you actually want. So dangerous. Round-off errors are not so interesting. In modern computers, you have enough digits, so this is not so any problem anymore. Also in the programming, again, that's really not up to us to find errors in the code. That would be too bad. But you should keep it in mind. Say now you're using OpenFOAM for rather sophisticated problems, and you get very strange results, and you don't know why. And then you Google on the internet, and then you discover that, okay, the OpenFOAM version 4 that we are using has a bug just for this problem. Okay, that would be very, very sad to present without telling people then I have used a program that actually has a bug and that explains my results. I mean, you are innocent, but it's your responsibility to check it. Is there a bug in the code or not? It's always bugs in the code, always. And of course, errors in the input parameters, also something that you have to verify that that's not the case. When you are doing a report, presenting some simulation, what you actually should do is provide enough data, input data, geometrical data, all your choices, so that another person later that reads your report should be able to do the exact same simulation that you have done and obtain the same answer. Your answers has to be reproducible, meaning you should provide enough data for the next guy to do the exact same thing that you have been doing. But as I said, this is maybe not something that belongs into the report, but it belongs in the appendix. You are limited to 10 pages only, and that's that can be hard. Trust me. Sounds like much, but no, it can be heavy. Yeah. So the models, of course, will also limit your say the accuracy of your results. Bad models, bad results, of course. Yeah, and this is also a danger. The commercial codes are built very robust. Now I'm talking the codes that you have to pay for. Fluent, CFX, Star CCM, very expensive, but they are also very, very robust. So whatever you do, you get an answer that may look actually quite okay, but it could still be rubbish. So that's the danger with these codes, that they are so robust that you can actually do anything. I think I've discussed this earlier. I tried it with, I think that was Star CCM. I made an inlet, and then on purpose I didn't make any outlet. And then I send in incompressible fluid. Of course, this is not possible. You can't send in anything. But remember, as a boundary condition, you can use 1 meters per second in, and then he will do it. And the code didn't explode, as it should. I mean, this is something that should go very wrong very fast, but it didn't. So for that reason, I said Star CCM is not a program that I want to use when he does stupid things like that. Or if you set in a negative viscosity, use a negative viscosity as an input value. If the code doesn't explode, throw it away. Of course, he should explode. If he's still stable and produces some results, let it go. It's not worth it. Of course, it should explode. So be careful with these commercial codes. Yeah, there you have it. So, I mean, you have a lot of these consultant companies that uses these codes, and it's sort of a It's a lot of legal aspects actually. When you have big companies, Statoil, oil companies, they use a lot of consultant companies to answer small problems for them. Say we need a pipeline here, so and so, and it shouldn't explode. Can you simulate this? And then the consultant company says, of course, and then they simulate away. One simulation without any checking, controlling, nothing, and then they report back, yes, this looks a-okay, and then Statoil build this thing and everything explodes and you have an oil leak. Who's in charge? That's the whole point. Statoil has done the correct thing. They have used consultants. That's quite okay. The consultants, they are not responsible for anything, so they are also not to blame. Nobody is to blame. That's the whole point. So that's a economic word for you. It's a terrible place. But actually they can get away with it. So no, I don't like these codes. Open foam, much better. If you do something stupid, it explodes. As you all should have experienced by now. Much better. So these commercial codes, terrible, awful. Don't pay it. Also here, the converged solution, of course, this is a concept for steady state case only. When you have a transient problem, you can simulate as long as you like. It's not necessarily that you have a steady state solution. Things may change over time continuously. But for a steady state code, then you sort of should converge, like using simple form, for instance. Then you set up maximum time step, that was 1000 time steps, but if he finds a solution before 1000, then he stops automatically, saying, okay, now I have a converged solution. It does not necessarily say that the answer is correct. That depends on a lot of things, like also what's the criteria for saying that it is converged and so on. So there you have to check a lot for the different codes, different input criteria when it is converged. So we have two sort of tools, two sort of concepts that we now need to address. It's called verification and validation. Verification, so the short description, solving the equations right. This, you might say, is the easy part. That's something that we can sort of test and access ourselves. Should be listed sort of short here. We can quantify it, check discretization, iteration numbers, round-off arrows, whatever. In a lot of different ways. So yes, it would be very nice then to be able to say the answer is 4.0 plus minus something. That would be very nice indeed. How can you do that, plus minus something? Not so easy in CFD, but yes, that would be very, very nice indeed. Okay, we know typically we have first order schemes, second order schemes, and so on. So at least an idea, an estimate of an error would be possible for us to find. So check the code, check the convergence, residuals, yada yada yada, and if you can, do some consistency checks, like a total mass conservation. Like in this problem, for instance, I mean, here I send in mass and nothing goes out. And if it's incompressible, then of course this is rubbish. What you must do then is to have an opening, so something goes out as well. And as a control, you integrate the kilos per second in and kilos per second out and see that they match. Then you have mass conservation. You can also talk about not momentum conservation, but call it momentum balance. That's Newton's second law for fluid mechanics. That's the Reynolds transport theorem. The sum of forces acting on any control volume or the fluid inside any control volume, what would it be? Well, it should be time derivative of the momentum inside a volume plus the surface flux of momentum out of your volume. So here volume integral, here a surface integral, and the forces, pressure forces, viscous forces, gravity, or even contact forces if you have the control volume then touching a solid wall. Here you could invent any volume with any surface. Inside here, for instance, you can design your own volume, whatever you want. If this equation here is not fulfilled, 2 plus minus something, then you haven't solved Newton's second law of motion. Then your answer is wrong. And you can pick any volume. You can take the entire domain if you want, or just part of it, or just one single cell. This Newton's second law of motion should be solved all over the place, at any volume size. I will put out an example for you for the problem exercise 5, where we had the flow around the cylinder, where I try with different control volumes, and just to verify that yes, I get the same answer. Also, in this exercise, we had open foam reporting the lift and drag forces for us. He had calculated them himself. We don't know how he has done that. We didn't check the source code, but we got some answers from him. Here, with this equation, we could have checked what is the lift and drag force here by checking the inflow and the outflow. Then we can take a control volume analysis of the whole thing, just to verify that yes, this is correct or this is wrong. So I'll put that one out for you later on. Grid convergence, that can be a trick, as you know. With turbulent flows, you can't really do grid convergence, finer and finer grid, and then see that your answer tending towards one value. With turbulence, finer and finer mesh gives you different answers every time. So this is for laminar case that we can have grid independent answers. Unless, of course, you can resolve the turbulent boundary layers, then it's possible. But with wall models, no. Temporal convergence, also something that has to be checked if you are using a transient code. Now validation. That is solving the right equations. So solving the equations right, that was verification to validate the whole thing. Then we need something to compare with. Has this simulation of mine something to do with real life, with Mother Nature? Then we need something to compare with. So if you find some experimental data, remember the data also has some plus minus values. So the idea here is to have maybe other simulations or experimental data to compare with, and then hopefully our result, our prediction is sort of inside the area, not far outside like this one. So finding something to compare with, very important indeed. So the process for validation, compare with experimental data or other simulations. Not necessarily a DNS, but hopefully a quite accurate simulation or other simulations that has been done and reported already. You can of course do several simulations yourself. That's also an option. Say you use OpenFOAM, and then you do the exact same problem with Fluent, for instance, and then you can compare these two. That's quite okay. You might risk, of course, that both are wrong. Then you're in trouble. Yeah. So we would have liked to have all the plus-minus data, yes. That's not always that they report them, so they can be hard to find, of course. But that would have been very nice, yes, to have these range of the data. And then you have the problem, you have no data available. So yeah, you have one other way to think, I would say. Say you want to do a simulation that is quite complex. The geometry is not that anybody has done before. A little nasty geometry maybe, or the Reynolds number range is a little strange, whatever. Then simplify, change your problem to something that has been done. Say you want to simulate the flow around, what should we say, an oil rig, for instance. Huge problem, large problem, three-dimensional, of course it is. So you have these huge legs, platform, and then maybe we have some towers here, some small buildings, whatever. So this is what you are going to simulate. Very complex, very nasty problem. How do you do this? Of course, you can have the 3D geometry inside a mesh generator, produce the mesh, start the simulation, and get some results. Yes, you can do that. But here you have nothing to compare with. This is something that is going to be built. Nobody has built it yet. So we have no measurements available. Then what do? Well, here I would have sort of split it up into several problems. Take the flow around one single leg and see how well can the code actually do the simulation around one single cylinder. How fine must the mesh be here? What kind of turbulence model should I use with this Reynolds number range? Then you do the same with, say, one of the buildings. Sort of a building that exists already, that has been done. You should find some examples for simulation there, finding drag data, for instance. And then verify that, yes, my code is capable of simulating around just one of these buildings. Then, if he can handle these two, then he should also be able to handle the combination. Then you have sort of validated your setup, I would say. If you don't find any data to compare with for the entire problem, break it up into smaller pieces and at least verify those pieces. Then the combination also should be good. Okay? Okay. Any questions? We take a break.